Okay, so our last talk for this week will be with Kenyon, who will talk about diamonds and why. Please.
Hi. Yes, thanks for the invitation, and happy birthday, Sasha. Thanks for all your friendship over the years that we've known each other. This talk is based on joint work with Dan Douglas, who I think is here. He's here, and Helen, she also here. So if you have any questions, they can also help. And I welcome questions or comments about the talk. So hopefully it's reasonably elementary. There's many different points of view on the stuff we've been doing. Each of us has our own sort of motivation. Let me talk about one particular motivating problem, which has been sort of in the back of my mind for a long time, but just for the purpose of this talk, maybe you can think of this as a motivating problem. We have a Riemann surface, and we're interested in constructing a probability measure on simple laminations. What's a simple lamination? I just mean a disjoint collection of closed curves on the surface, like in blue there. And that's a simple lamination, and we are going to just, you can think of what we're doing here as describing a certain natural probability measure on simple laminations. And in fact, if you're not a probabilist, it's much simpler to just think about isotopy classes of simple laminations, right? Because the actual curves themselves are going to be kind of nasty and fractal. But if you just think about the isotopy classes of simple laminations, then you get, just some discrete objects, a discrete set of objects because of course there's like a countable collection of isotopy classes. And this particular, so what do I mean by probability measure? I'm just going to show you how to select one at random. And the goal is to sort of describe, compute various probabilities of various events for this probability measure. And I want to convince you that this is a natural probability measure. I probably won't convince you of that, but at least you will see that it is natural in the sense that it arises from the determinant of this sum operator, the D-bar operator. And this is not a, I mean, there's a related idea going back to a very, very important and mysterious formula, the Selberg trace formula, which relates the determinant of Laplacian to on a closed Riemann surface to a certain sum of over the closed geodesics on that surface, some function of the length of the geodesics. And so we're doing something kind of similar, except that we're, instead of summing over geodesic, we're summing over simple laminations. But it's still a determinant of a certain operator. Okay. All right. So here's sort of an example of a calculation we can do, which comes out to have a nice answer. Let's just take our surface to be a torus, right? In fact, just a square torus. Now, what is a simple lamination on a square torus? It's just a collection of k parallel curves in some homology class I and j, where I and j are relatively prime. And what's the probability of that? What's the probability of that event? What it's going to turn out to be? I mean, this was worked out 13 years ago by Boutillier and Boutillier. Comes out to be this very nice, friendly formula, e to the minus some constant times k squared I squared plus j squared, right? Where the denominator, of course, is this theta function. So the point of this calculation is that you get some interesting number theoretic quantity underlying this probability measure.
You say they worked it out on which assumptions?
Yeah, I haven't told you anything. I haven't defined anything yet, right? I'm just sort of giving you a preview of the answer. And now I'm going to spend the rest of the talk discussing what this particular measure is, where it arises. Okay, but yes, thanks. Okay, so it's coming from some stat mech model, which is the dimer model, which we've heard about before, even in Lawrence talk. What's a random dimer cover of a graph? So we have an underlying graph here. In this case, the graph is the square grid for this on this slide, n by n square grid. And the dimer cover is just a perfect matching. So you just pair up each vertex with one of its neighbors to make a perfect pairing, perfect matching. And if we want to count the number of dimer covers of a graph like that n by n squared grid has a sort of an exponentially large number of dimer covers, like exponential in the number of vertices. But there is kind of a beautiful combinatorial method for counting the dimer covers. Maybe everybody knows this method, but let me just tell you here again. You construct this matrix K called the Castellan matrix, just like the one, it's the same one that was in Lawrence talk. Is just an adjacency matrix of the graph. Well, it's an adjacency between the black vertices and the white vertices, since the graph is bipartite, except there's some signs involved. So you can see that, it's got rows indexing white vertices, columns indexing black vertices, and the entries are 0 if they're not adjacent, if the vertices are not adjacent, and otherwise they're plus or minus 1. And the signs are arranged in, well, there's some rule defining the signs. You arrange the signs so that the theorem holds. And it's not so important what the exact rule is, but let me just tell you that around a face, around a square face, you have to have an odd number of minus signs, and around a face of length L, you need L over 2 plus 1 mod 2 minus signs. Once you have found such a matrix, then the theorem of Castellan, and also jointly, independently by Temperley and Fisher back in the 60s, the number of dimer covers of the graph is just the determinant of this matrix, absolute value. Okay. Well, what I'm going to do is now, here's a picture of a dimer cover. If I bring in another dimer cover, independent dimer cover, I take a random dimer cover in blue and I take another random dimer cover in green, and I just draw them on top of each other and then forget the colors. I'm going to call that a double dimer cover, or a two web. It just means that at every vertex it's a subgraph such that at every vertex there's 2 edges coming into there. Then, once I forget the colors, I get a sea of loops, a collection of loops, simple loops and double edges in the graph. And there's a natural measure on the double dimer covers, which is induced from the uniform measure on the single dimer covers. If I take 2 single dimer covers and I superimpose them, you see that for every loop, there's sort of 2 ways you can. It can be colored. It can be colored green, blue, or blue, green, blue, green. And so each loop, in some sense, contributes a factor of 2. So when you want to talk about the natural measure on double dimer covers, you should give each loop a factor of 2. The probability of a double dimer cover, at least with respect to the natural measure coming from the single dimer cover, the uniform measure on single dimer covers, for a double dimer cover, the probability of a configuration will be proportional to 2 to the number of loops. Oh. So the doubled edges don't count as loops with respect to this formula, because a doubled edge there's only one way to cover that with the 2 edges. Anyway, those don't give you a factor of 2. All right. So now the goal, one goal, sort of a combinatorics motivated goal, is to understand something about this sort of sea of loops on a very large graph. And one sort of observable quantity we can get is we can define doing the following. Let's puncture the graph at some faces or fix some particular faces of the graph, like those three ones indicated with a star. And then we can ask, if I take a random configuration here, random loop soup, what's the probability that that there's a loop in the complement of those? I mean, what's the probability that there's a loop in the double dimer cover, which has a particular homotopy class with respect to those stars? So if you think of the puncturing the plane, now I have a punctured Riemann surface, plane or a disk punctured at a finite number of points, and I can look at the corresponding simple lamination in the complement of those punctures, I mean, on that Riemann surface, and ask what's its isotopy type, right? And sort of right. So the interesting question that we would like to answer is, what's the probability of a particular lamination type when you superimpose these two single dimer covers? And you know, this theorem is the sort of important step in sort of convincing yourself that this is an interesting question. So this is a sort of work of several authors, you know, making it, you know, anyway, this was something that I worked out in 14 and then was sort of corrected by Julien Dubeda and then these two authors later, that these, you can try to make a scaling limit. If I fix a plane domain or some Riemann surface, it also works on a Riemann surface, but you know, it's somehow easier to state in a planar domain. These the probabilities that we're computing, the probability of any simple lamination has a nice limit in the limit when the mesh size of the graph goes to 0. So if I fix my domain or fix my Riemann surface, fix my punctures, take a sequence of graphs where the mesh size epsilon is going to 0, then these probability of a given lamination will converge, and as epsilon goes to 0, and in the limit they will be only depend on the conformal structure of that domain or that Riemann surface. So that's that indicates that we are constructing in some way some sort of conformally invariant loop system on that surface. So how is this result proved? Well, how do you compute these quantities? Well, we're going to put an SL2 local system on our graph. What does that mean? It just means that we have a two-dimensional vector space associated to each vertex, and along every edge, I have a sort of a parallel transport, which is just an isomorphism between the copies of the vector space there. If you like, it's just a 2x2 matrix in SL2 associated to each edge, to each directed edge. That's an SL2 connection on the graph. G is my graph. And of course, on my Riemann surface or on my punctured disk, I'm going to consider connections which are flat. So they have trivial monodromy around contractible faces. The monodromy is just the composition of the parallel transports around a loop. Yes?
Before the continue, the previous slide. What if you have two loops?
That's fine. I'm computing the probability of a simple lamination, which is a finite collection of simple loops. Maybe I'm only interested in the probability, the existence of a single loop, or what if I want 17 loops? I want that probability as well. So every event will have a different probability. Okay, so now, for every loop gamma, let me just fix the notation here. If I have a loop gamma on my surface, I can let phi sub gamma be the monodromy of the connection along gamma. Well, my loops are not a priori oriented. So if you like, you could choose some orientation and let phi gamma be the oriented version of that. Although then I'm going to define the trace, which won't depend on the orientation. So what's the trace? If I have any double dimer configuration M, just like in the previous slide, any configuration like this, I can take the product over all the loops of the double dimer, all the double dimer loops, take the trace, take their monodromy and take its trace. And of course the trace, I mean, the nice thing about SL2 is that the trace of a matrix and the trace of the inverse matrix are the same, so the trace doesn't depend on the orientation. Since the loops are unoriented, the trace is still well defined. That's what this comment is about. Also note that if I have a trivial loop, if I have a topologically trivial loop, its trace is 2 because the monodromy is the identity, the trace is 2, and so this generalizes the formula when the connection is the identity. Remember I said at the beginning that each loop should count 2. Now each loop is counting either 2 or the trace if it happens to be topologically non-trivial. So our underlying goal is to understand what happens when our connection is trivial. It's just the trivial connection, the identity connection, but we can use the non-identity connection to detect topological properties, to detect the homotopy type of the loops. That's assuming that we can somehow compute the corresponding partition sum here in the presence of a non-trivial connection. So I first defined the Castellan matrix using just the identity matrix or just a scalar as a scalar matrix. But now we can augment the Castellan matrix to when we have a non-trivial SF2 local system. How do we do that? I'm going to now define a new Castellan matrix where the entries are just defined as before. It's like the adjacency matrix, except that each entry is going to be the monodromy along the corresponding edge, phi WB, with some sign, which is still given by those Castellan signs, the plus or minus signs from before. Right, so, and just to make sure we're all on the same page, here's a very small example. I got a 2x3 grid, and on the, ignore the surface for now. On each edge, I've got some 2x2 SL2 matrix, like A here, B there, and so on. Then I can make this Castellan matrix whose rows are indexing the white vertices and the columns are indexing the black vertices. It's a 3x3 matrix, but the entries are, it's a matrix of matrices because the entries are now in SL2. Any questions? Yes.
Is the analog of the sign?
Yeah, you use the exact same signs as we did for the scalar matrix around each face. If I did it correctly, right around the face on the left, I have to have an odd number of minus signs, and I think the 2-2 entry has a minus.
Sorry, it also contain entry 0.
Yeah, that 0 should be a 2x2 matrix of zeros.
Nothing in SL2.
That's correct. So it's really a matrix of 2x2 matrices, which are not necessarily in SL2. Yeah, you can also have parallel edges between two vertices, and then when you sum two matrices in SL2, you won't get something in SL2. Nonetheless, there's an analog of Castellan's theorem in this case, which is that the determinant of this matrix, well, we had this matrix of matrices, but I could just erase all the inter parentheses and make it a matrix of twice the size of scalar entries. Just take the determinant, and it counts exactly what we want, what we were hoping for, which is it counts the sum now over all double dimer configurations Right before it was a sum, the determinant of the scalar matrix was the sum over single dimer configurations. Now the matrix is twice the size and it's counting double dimer configurations, and each configuration contributes its trace, where the trace, remember, is the product over the loops of the monodromy, of the trace of the monodromy around the loop. And in particular, if you plug in the trivial connection, everybody's the identity, then you indeed recover the right. So the trace of a configuration is now 2 to the number of its loops, and you recover the original double dimer partition function. Okay. So this is a little bit, I mean, this takes some, this is a little bit non-trivial. I mean, the original Castellane theorem involves a little combinatorics about dealing with the minus signs. Likewise here, this involves some dealing with some more minus signs, but it's not that hard. But here's what we can do now. We're not interested in all possible, if we want to understand the isotopy classes, we can regroup that sum. That sum is at the top there is a sum over all possible double dimer configurations. But we're interested in only the isotopy class. So we can regroup this sum here into the sum over isotopy classes of simple laminations, right? And because the trace here as a function of the connection only depends on the isotopy class, except for the trivial loops, which contribute powers of 2. And when we regroup the sum this way, we've got a sum over all, yeah, so capital lambda is the set of isotopy classes of simple laminations. And there's this coefficient C lambda, that's the coefficient we were sort of asking for. The meaning of C lambda is, well, up to this constant of proportionality, that's the probability that a random double dimer configuration has the desired isotopy class. So here we're in a good setting because we have this object which we can in principle compute. It's just a determinant of some big matrix, and we need to expand that over with respect to these functions trace of lambda, and the magic theorem of Fock and Goncharov, which really follows from Peter Weil theorem, I guess, is that the traces of simple laminations on a Riemann surface form a linear basis for the, well, regular functions on the character variety, which is the functions that we're dealing with. So these functions here, trace of lambda, where lambda runs over simple laminations, those are linearly independent. And therefore, in principle, we can extract these coefficients C lambda from this expression, right? I can compute the determinant. It's just my computer at least can compute this determinant. And by the linear independence of these functions, I can extract the C lambdas. I'm looking at that. I have a surface, possibly a punctured surface or a closed surface. I look at all the representations of the pi1 into SL2 in this case, and I quotient out by the conjugation. That's the character variety. Okay, so yeah, that's the corollaries that at least, you know, to the extent that, I mean, with at least my computer could in principle compute these coefficients. But the problem is that, you know, if I have a very large graph, this is a large sum with lots of terms. We don't know how to, there's no sort of orthogonality between these functions here. So we don't know in principle how to extract the C lambda. That's kind of an open question which we are grappling with. We're still grappling with. Only in special and only for very small surfaces can we actually, you know, do this at the moment. All right. In particular for the torus, this is, I'm just repeating the slide from before. Suppose I have a torus, and I have a square torus, and I could take a very fine square grid there with a mesh size epsilon going to 0. I take a random double dimer cover, and I ask, what's the probability that I have, you know, like 2 loops in homology class 1, 1, or something like that. And the theorem of these guys is that I put before is that the probability of this kind of event that you have, some set of curves in a homology class ij is in the limit as epsilon goes to 0 converges to this beautiful simple answer. And of course, if the torus is not square, there's also an answer. It's just I didn't want a very similar answer.
So the normalized this probability.
Yeah, that's what that denominator z is. The z is the sum over all the possibilities to make it a probability measure. Hopefully, I didn't screw up because I think that sums to 1. I may be missing a factor of 2. What? Okay. Any more questions? All right. Now we're going to go to a higher rank setting. Rather than just take 2 dimer covers, I'm going to take n dimer covers, n bigger than or equal to 2 or bigger than or equal to 1 if you like. And here I just drew a picture with 3. I took 3 different dimer covers and I superimposed them. I drew them all on the same graph, 1 red, 1 blue, 1 green, 3 dimer covers. And when you superimpose them, you get a more complicated type of object, which we call a multi-web, an n multi-web if you have n dimer covers. So this is a picture of a 3 multi-web. Well, this is a colored 3 multi-web. If you forget the colors, then you get a 3 multi-web. It's a subgraph. It's a collection of edges with multiplicities, a multi-set of edges, if you like, with degree n, which means that at each edge gets assigned a non-negative integer, and at each vertex, the sum over all the edges incident there of the integers adds up to n. So it's like a degree n subgraph, except that you're allowed multiple edges. That's called an n multi-web, or if you like, it's the same as an n-fold dimer cover. And I'm going to call capital omega n the set of n multi-webs. So in particular, a double dimer cover is just a 2 multi-web, and a single dimer cover is a 1 multi-web. So this is a natural generalization. And the main result is that with Dan and Howlin is that you can define the Castling determinant just as we did before when you have a SLN local system on your graph. Okay, so there's some, if capital Phi defines an SLN local system on your graph, you can make the Castling matrix K tilde as before. Its determinant up to a sign counts all n-fold multi-webs with their trace. And I haven't defined the trace of a multi-web yet, so I'm going to do that now. Right, so this is the sort of main combinatorial result. This is all some sort of combinatorial keeping track of signs. That's the hardest part, is keeping track of the signs. But let me define what the trace of a multi-web is. What's the trace of an object like this when you're in the presence of a SLN local system? Okay, and I'm just going to give you the picture for n equals 3. You can generalize to general n, but this is already contains most of the, essentially all the difficulty. So we have this subgraph. We have a graph of degree 3. And each vertex has degree 3, possibly with multiplicity. And I've got an SLN. I got a rank n bundle, an Rn bundle on the graph. So at each vertex, I've got a n-dimensional vector space, and on each edge, I've got an SLN connecting those vectors, SLN matrix connecting those vector spaces. So what we're going to do, let me point to the screen here. We're going to take a copy at each white vertex. I take a copy of that, in this case, 3-dimensional vector space along near that vertex on each edge. And likewise, at the black vertices, I'm going to take a copy of that vector space, but I'm going to think of that as the dual vector space on each edge. So now on each edge, there are 2 n-dimensional vector spaces, one located near each endpoint. Okay, and right, so in the case n equals 3, it's a 3-dimensional vector space. It's got some basis, standard basis E1, E2, and E3. Now I can define at each vertex, at the white vertex, I'm going to define this vector inside the tensor product of those 3 vector spaces. So there's 3, sorry, the annoying thing about this theory is that there's 3 vector spaces, each of dimension 3. So you have to keep track of which index means what. So the upper index means the vector space, which vector space is in, and the lower index means which basis vector I'm dealing with. But inside the tensor product here, there's this object called the codeterminant inside the tensor product of those three-dimensional vector spaces. Let's call that V sub W. That's the codeterminant. You do it likewise at a black vertex. You have a codeterminant with the dual basis vectors, and then you just contract this guy. You take the tensor product over all the vertices, and you contract along each edge using the matrix. So I can write it in this way. So you take the tensor product over all the white vertices, the tensor product over all the black vertices, and then you contract these two with the SL, in this case, SL3 matrices along each edge. So that's,
I don't know where to put V, where to put V star. On the goal?
yeah, at each white vertex, I put V, and at each black vertex, I put V star. So I mean, well, one of these, this is like the, well, maybe I got it backwards. This is the vector, and that's the dual vector, or vice versa. Is that okay? Oh, well, it's kind of mysterious. Let me do an example.
You
Yep.
put some sign rule.
Yeah, oh yeah, this is,
You allow pentagons in your cell, right? Now you cannot.
pentagons?
You had a sign rule something L over 2 plus 1.
Oh, yeah.
over 2.
Yeah, that's not part of the definition of the trace. The trace is, it doesn't depend on those Castellane signs
But
yet.
now you have also black with white coloring, so your L is always even, right?
Yeah, all the graphs are bipartite.
Oh, I see.
All the graphs in this talk are bipartite. Yeah, here's a little example of a trace of a 3-web, right? I've got just 2 vertices, 3 edges between them with parallel transports A, B, and C. Those matrices are in SL3. And now at the white vertex, I've got this codeterminant, which has 6 terms. At the black vertex, I've got a codeterminant which has 6 terms. So when I combine, when I pair them, I'm going to get 36 terms. For example, when I pair the first term and this of this sum and the first term of that sum, right? You see, I've got the E1 here and the F1 there. That gives me the RR entry of A. Here I changed 1, 2, and 3 to R, G, and B, just so I could remember that these lower guys are the indices of the basis of the vector space, and the upper guys are telling me which edge the vector lies on. Anyway, it's not so important. When you work this out, you get this, the trace is now a sum of these 36 terms, which you can write in a much more compact form as this trace of this actual trace of matrices. If I take AB inverse, trace of AB inverse times trace of CB inverse minus, AB inverse, CB inverse, right? There's some, these individual terms correspond to some loops in the graph. Traces of actual monodromies of loops in the graph. So what you see is that the trace of the web here, the trace of this web can be written as a sum of traces of loops in the graph, but it's a little bit non-obvious what that sum is. If this expression doesn't even look symmetric in A, B, and C, but you can write it in a symmetric form using a determinant. You take the determinant of XA plus YB plus ZC, where X, Y, and Z are just variables, and then from that polynomial, you extract the XYZ coefficient. That will be this expression. And there it's kind of obviously symmetric. Any questions about the trace? So there's this kind of slightly mysterious thing, the trace of a web. I define it for 3 webs. It works as well for n webs. Let me give you a slightly more combinatorial way to think about that trace. I mean, it's really the same as just reinterpreting it in terms of colorings, which is sometimes useful. I have this, so now what we're going to do is I'm just giving you an alternate way to think about the trace, because the trace, if you haven't seen it before, it's a little bit mysterious. Here we go. We're going to assign colors in 1 through n to the half edges at each vertex in such a way that each vertex, so what I'm going to do, here's this is my, I'm taking the example with n equals 5. So now I've got a SL5 local system, and I want to compute the trace on this multi-web of the 5 multi-web. So at a vertex there, this, you know, each edge has some multiplicity. In this case, this edge has multiplicity 2, that one has multiplicity 2, that one has multiplicity 1. And I assign a subset of colors of size equal to the multiplicity. And then I want to make sure that each color gets used exactly once around each vertex, right? So I could assign colors 1, 3 here, 2, 4 there, and 5 there. And likewise at some other assignment at the other vertices. And then once I've assigned the colors around a vertex, then along that edge, I've got some parallel transport in this case, SL5. I take the corresponding minor of that matrix. So this is the parallel transport, and I take the 1, 3, 2, 5 minor, because the 1, 3 are the colors here and the 2, 5 are the colors there. And then I just take the product over all those minors over all the edges with a sign, with an appropriate sign, and then I sum over all colorings. That's the trace. So the trace can be written as a sum over all choices of colorings of some product of matrix minors. And the sign here just depends on the permutation of the colors around compared to some, you know, cyclic permutation of the colors here. Well, it's not so important what the sign is for now. Let me just leave it at that. Okay. Here's the statement. Now I can state the theorem again. It's the same theorem I put up before. Now you know sort of what the right-hand side is. Each n-fold multi-web has a certain trace, which is this complicated sort of tensor invariant, and the determinant of the Castellane matrix counts all configurations with their trace. And if you're worried about the global sign, this is kind of an unavoidable thing. It's a slightly artificial, right? When n is odd, the sign, well, I mean, the sign of the determinant, because the rows and columns are indexing different sets, it depends on how you order the rows, the sign of the determinant. When n is even, the determinant doesn't depend on that order, because every entry is an even matrix, but the sign of the trace will depend on some artificial choice of the ordering of the, I mean, it depends on the sign back here, which is not so important. Okay, anyway, let's move forward. We have this nice theorem which says that the determinant is a sum of these traces, but we don't have the analog in general of that Falcon-Goncharov theorem that says those right-hand sides are independent as functions on the character variety. But that's because typical multi-webs are not reduced. There's a, at least for n equals 3, there's a nice theory about using reduced webs. A 3 multi-web is called reduced or non-elliptic if there are no contractible faces of degree 2 or 4. And the theorem of Sikora and Westbury that says that traces of the reduced webs do indeed form a basis for regular functions on the character variety, on the SL3 character variety. So at least for n equals 3, we still have some remnant of that Falcon-Goncharov theorem, I mean, here, except that we have to deal only with reduced webs. But fortunately, there are some reduction rules, skein relations, which allow you to take a general web and reduce it. I mean, rewrite it as a linear combination of reduced webs. And those are the SL3 skein relations, which are all a consequence of that first skein relation. So ignore the blue things which just tell you how the parallel transports transform. But the basic skein relation is you have this 3-web, which is a trivalent graph, and you can replace it with a linear combination of 2. Right, if I've got a 3-web, which is some complicated trivalent graph, and it's got inside there, it's got 2 adjacent vertices which are joined by an edge. I can replace that with those 2 inside that. I can just do a local replacement. With these 2 webs. Unfortunately, one of them has a crossing. And these webs will have fewer vertices. And so you can use this to use these local operations to rewrite your given web that you started with, complicated web you started with, eventually with a bunch of reduced webs at the bottom. Well, except that what does it mean to be reduced if you have crossings? Well, if you're
Before, you still use the notion of the face of the web. What's the face of 3-web?
what's the face?
Yes, on the previous slide.
Yeah, no, that's right. Yeah, like here. Well, this 3-web has faces. The graph is drawn on a surface, and so it makes sense to talk about a locally planar graph. And that one has faces. Is that what you're talking about? No? Yeah, you don't talk about faces when you have. So I'm not going to do this skein relation. I'm going to do this set of skein relations, which are all consequences of the above one. And well, except for maybe the first one. If you want to preserve local planarity of your web, you can reduce. It's a theorem that you can reduce any web using these rules to a linear combination of locally planar reduced webs. And any loop you can just remove it from the web and multiply the web by 3. I mean, it's an operation on formal linear combinations of webs, if you like. And a bygone can be you just throw it out, replace it by a single edge with weight 2, as long as the bygone is topologically trivial. So there's no monodromy around that loop. And likewise, if you have a square with no monodromy, then you can replace it with 2 webs, either going this way or that way. Okay, so those obviously preserve planarity, and it's a theorem that any locally planar web on the surface can be reduced using these operations to a linear combination, positive linear combination of reduced webs. And back to that's what I wrote here. If I have a 3 multi-web, possibly complicated 3 multi-web on a surface with a flat SL3 connection, I can reduce it. I can rewrite its trace. Right. The point of these skein relations is the trace they preserve the trace in the sense that the trace of the before web is equal to the sum over the reductions of the traces. So therefore, we can take this determinant of our Castellane operator, which was originally a sum over all these complicated webs. Each of those webs can be reduced to a linear combination of reduced webs, and therefore we can rewrite the determinant as a sum over isotopy classes of reduced webs with some coefficients again, C lambda. And that theorem of Sikora-Westbury says that again, when you're talking about reduced webs, these traces are linearly independent. So you can in principle extract the coefficients C lambda. Yay. Right. But again, we're stuck, right? How do you it's a linear algebra problem at this point, right? We got this expression we know what all the traces are. I mean, in principle, we know what traces are. How do we extract the coefficients from this big, potentially very large polynomial? All right, another problem here, which I didn't even talk about. It's oh yeah, I did talk about it. It's right there. Well, here's an issue, which is that you can take your complicated web and write it as a linear combination of reduced webs, but there's no canonical linear combination of reduced webs. If you do the reduction in a different order, you get a different set at the bottom, a different set of reduced webs. However, even though the reduction is not canonical, doesn't lead to a canonical set of webs, that the isotopy types of the webs that you get at the bottom are well defined. So you always get the same set of isotopy classes, but they may be slightly different because of there's some non-commutativity in the way that you do the reduction. And so that's a kind of a mysterious thing, is that we're not, unlike the SL2 case, we're not talking about some specific fixed reduced webs at the bottom. We can only talk about the isotopy classes, not the actual webs themselves. All right, and just to show you that we can carry out this process in some simple graphs. For example, an annulus, right? That's like the simplest graph that has some non-trivial topology. And it's not hard to show that every reduced web, 3-web, is just going to be, in this case, it's just a union of loops, oriented loops, topologically non-trivial oriented loops. So we have an annulus, and every reduced web is just going to be a loop winding clockwise or counterclockwise around the annulus. Therefore, when we compute the determinant of our graph on the annulus,
in which sense it is the 3? The blue guy, it doesn't look like.
Oh yeah, you're right. Yeah, you're right. That's my fault. Let me explain. I've got a 3 multi-web loop. I mean, could look like this. What? It's a ring which has alternate multiplicity 1 and 2. And I can give an orientation, which is I orient the single edges from white to black, and the other, and that defines an orientation. So if I had the alternate, right, this one would be oriented that way. If that's a white vertex, that's a black vertex. Okay, so every loop on an annulus looks like this 1, 2, 1, 2 multiplicity sequence of multiplicities. Thank you, Andy. All right, so when we do that, we've got it on an annulus, we just have one monodromy, which is A. It's a flat connection on annulus. It's just one monodromy A going around the annulus. The determinant of K depends on that single matrix A, and just depends on the trace of A or its inverse. Right, so in this case, a reduced multi-web has I things going clockwise, counterclockwise, and J things going counterclockwise. So there's just these 2 indices which describe all reduced webs. And so, you can do the calculation easily enough in this case. If I have an n by m grid on a cylinder, right? That's like the simplest graph you might think of on a cylinder. You take n and m going to infinity, where their ratio goes to some modulus tau, then that determinant has a kind of a nice product form. Here U is the trace, I put U for trace of A and B for trace of A inverse, has this nice form where Q is the conformal modulus of the cylinder. It's kind of a pretty expression. So if you want to know the probability that your random triple dimer cover has a particular reduced web, then you have to extract the U, the corresponding coefficient from this infinite product. that make sense? Okay, well, what's the next step of the surface is a torus, right? We could work out the case of the torus for SL2. For SL3, we're stuck. Why? Well, there are lots of webs. There are lots of possible webs on the torus. I could take any, if I take this infinite honeycomb graph and I take any index, I mean, any periodic sublattice like this one, that if I take that parallelogram and I glue opposite sides together, I'll get a torus, and that black structure will be a web on the torus. That'll be a reduced web on the torus, which is much more complicated. It's got a whole bunch of honeycombs in it, a whole bunch of hexagons in it. But I don't know how to write the trace of that web as a function of the monodromies. So now I'm going to have two monodromies, A and B, which commute with each other. How do I write the trace as something I recognize, some sort of polynomial in the matrix entries, in the eigenvalues? So that's kind of where we're stuck for a torus, because already for a torus there are lots of webs. I mean, there are not that many. They're just indexed by these pictures, but I don't know how to compute the trace. And likewise on a pair of pants, that's another potentially very simple surface. A pair of pants is just a disk with two holes. Then there are also these complicated webs which you came from the honeycomb by, well, okay, you can see it here. You take this honeycomb, you take this parallelogram in there, this equilateral parallelogram, and you glue it as shown, and then you puncture the corners of that triangle. Then you get a pair of pants and a particular web on that pair of pants. But I don't know how to compute we haven't figured out how to compute the trace, even though it should be some reasonably friendly polynomial in the matrix entries. So that's where we're stuck now. And I will stop there. And thank you, Sasha. Happy birthday.
Any questions?
Do you expect the probability measure you get on the isotopic classes of reduced webs to be conformally invariant?
What?
Conformally invariant, or have a scaling limit?
Yeah. Yes. Right. In SL3, likewise, one would expect a conformally invariant object. That's something which only depends on the conformal type. We saw that in the case of the annulus here, right? The probability measure in the end only depended on this one parameter Q, which was the conformal modulus of the annulus. And I expect that same form. You'll get the same. I think we can prove in this case that we get the same formula for any annulus of conformal modulus tau. So yes, thanks for the question.
You said that you get a basis of something characteristic, right? But it seems like your formula depends only on the number of clockwise and counterclockwise loops and doesn't depend on their order.
That's right. Yes. Right. So the question is, can we? I mean, if I change the order of those loops, will I get a different probability? And at the moment we can't control for that order. Dan or Helen, do you know if we? The trace certainly doesn't care about the order. So that's an observable which our methods can't figure out right now. So
I have a question about like how much does this identity depend on the choice of grid? Like instead of like a square grid, can you choose a different grid to do the diamond covers and?
Oh yeah, there's a certain universality going on here, which I didn't talk about, but it doesn't depend on the fact that we used a square grid. Everything only depends on the conformal structure, as long as your grid is, well, you start with an annulus, right? It can be a sort of arbitrarily funny annulus. And you have to put your graph on there, whatever graph you choose, it has to be conformally embedded in a certain sense. I mean, you're going to have this graph with mesh size epsilon going to 0. And there's a certain notion of conformal embedding of the graph. If you embed it correctly, then you will get the same formula there.
Then, for example, a hexagon graph would be easier, so that you don't have this sign issue.
Yeah, that's right. It's easier, but it's harder to compute the determinant afterwards. Right. The nice thing about the square grid is it has this nice symmetry. That square grid on a cylinder, it's got this nice symmetry, so it's easy to compute the determinant.
So in the very first slide, there was this determinant of dz, I guess, and that you connected by the trace formula to what you're doing. I mean, can you go back to that and like say what is the precise statement, and can it be generalized to this SL3 story?
Right. I think what you're referring to is on the first slide, I had this D bar operator.
Sorry, yeah, DC bar.
And the Castelli matrix is a discrete version of that. It takes a while to understand why, but I mean, you can I can refer you to some references, but
is it just a kind of heuristics, or can it really be?
No, there's a well-defined sense in which this guy converges to that. This operator converges to that in the scaling limit. There's a well-defined sense of I mean, I'm sure there are many ways to discretize this guy, but the Castelli matrix is a very natural one which has occurred in physics by Castelli, and this one actually does have in the limit epsilon goes to 0 has the elements in the kernel of this are analytic functions and so on.
But for things that appear later in the talk with SL2 and SL3, there is also such an expression for the conformal limit.
Right. Right. When you have SLN, you have a Castelli matrix acting on sections of this thing, and there's a corresponding. I assume that there's a corresponding version of the D bar operator acting on sections. I didn't think about that. I didn't think about this point of view yet, but I assume that there's an analog. I mean, this guy is certainly well defined. What the meaning is in the scaling limit is less clear to me, but it's something to think about. It's a good question.
Thanks.
Okay, then yeah.
You asked several times this question, how to extract the C lambda.
Yes.
What kind of techniques are available? Like, for example, you mentioned this earlier work of Boutillier and someone else.
Yeah. So, right. If the group is small, in this case, the group is small enough that we can just use some Fourier basis to extract the coefficients. Right. If I give you this function of two variables u and v, it's easy to extract the coefficients. But and Falk and Goncharov discuss in their paper and a different basis for these functions, which are orthogonal in the Peter-Weil basis, essentially. But there's a sort of an upper triangular matrix which transforms the Peter-Weil basis to the trace basis. Well, I'm talking about SL2 case, and that we don't know what the coefficients in that upper triangular matrix are in general. If we knew that, we could do this extraction, but so there is this nice orthogonal basis in the background, which we'd love to use, but there's a little bit of combinatorics missing to figure out this upper triangular matrix of transforming one basis to another, because it's an infinite basis. There was a question on.
Yeah, please speak if there are a question on Zoom.
Vladimir?
Yeah, I may ask.
Yes.
Do you hear me? Okay. Yes.
Yeah.
I have two questions. First is the conformal structure and SL2 connections are just two things of the same nature. So there is a bit, for conformal structure, you can associate SL2 connection. So the question, if your partition function is essentially kind of symmetric with respect to if you exchange these two arguments, or one can say something about that. So the conformal, if the conformal invariant somehow comes from that, or
I'm not sure I understood the question. Are you asking about the conformal invariance?
Your partition function depends on two things: on conformal structure, in the limit, of course, in the
Yes.
limit of.
It depends on the conformal structure
small
and
mesh.
the connection.
On SO2 connection, for example, SO2. Well, not for just consider SO2 connection.
Yes.
But on the other hand, for any conformal structure, you can associate the SO2 connection. Just Fuchsian,
Yes.
well,
like the
constant
hyperbolic
curvature.
Right.
You have like hyperbolic structure, yeah. So you have your partition function is function of two arguments, which you can consider both as well SO2 connection.
Yeah.
The question if this partition function is symmetric with respect to these two arguments, or it has any chance to be symmetric.
Oh, that I don't know. That's a good question. I mean, one sort of possible approach to these questions, like this one, or maybe not that one, but like this one, is that at least in SL2, right, that we can sort of understand the conformal structure on a pair of pants is, determined by some boundary lengths. Is it possible to draw my web in a geodesic way somehow so that the trace is related to the geometry? Can I relate the trace of this web, which is, after all, a function of some, sorry. So here I'm talking about SL3, but inside SL3, there's of course one of the irreducible representations of SL2. And so is it possible that the trace for the SL2 is somehow related to the geometry of that web when you draw it in a geodesic way? And I can look at that web and try to minimize it, right? I mean, that's what happens in the SL2 cases. If you have a geodesic, if you have a simple lamination, you can write it as a hyperbolic, hyperbolic lamination. And then the lengths of the geodesics are, the lengths of those hyperbolic lengths are related to the traces. Is there an analog of that in the SL3 case? Well, I don't know. Does that partially answer your question, Elijah?
Well, yes, somehow, yeah.
Somehow.
And the second, yeah.
Go ahead. Go ahead.
Well, second is rather a comment, which I don't know if it makes any sense. So, some years ago, I made some conjecture which turned out to be wrong, but not too wrong. So about the orthogonality of these laminations. So they are not orthogonal, of course. You may ask, what is the dual basis?
Yes.
So if you have dual basis, it's sufficient to decompose. So first of all, what is natural scalar product between the two? So if you write your laminations length, this trace in cluster coordinates, it's just some Laurent polynomial with positive coefficients. And there is natural scalar product. You just multiply two Laurent polynomials and take the coefficient of 1. My conjecture was that the dual basis is just a very stupid one. You just take every Laurent polynomial and just inverse it. So you take 1 over Laurent polynomial. It's not longer Laurent polynomial. It's something infinite, of course. And moreover, it's not very canonically defined because it depends on which variable you start with decomposing. But something like 1 over, for example, 1 plus x transforms into 1 minus x plus x squared minus x cubed, etc. So it will be infinite polynomial. But nevertheless, if you compute what I did, I computed it on a computer, and it turned out that I had the impression that they are just orthogonal. But after Sean Keel explained that it's wrong and they are not all orthogonal. But anyway, you have plenty of zeros if you compute that. So there is maybe it can be used to decompose onto a basis.
Yeah, that sounds like a very interesting idea. That sounds like a great idea. We're open to any ideas about this problem, and I'm happy to explore that one. I just didn't. That's the first I heard of it. So, thanks.
Actually, Sean Keel in his paper he wrote about that much better than we did anywhere. So this is.
Yeah, maybe you could send me the reference.
I'll maybe send you a reference for that. Yeah.
Great. Thanks.
Okay, are there any other questions?
If there are no other questions, I would like to say a few words. So this conference. Huh? What?
We have to thank Rick.
Okay, let's thank Rick again.
That's fine.
So this conference was organized. So this is kind of the end of the in-person part of this conference, and there will be one more day in Zoom, but it's easier to say something when you see people. So this conference was organized by two of my former students, Linghui Shen and Daiping Wang, and two of my current colleagues, Ivan Losev and Andy Naitsky. And of course, I'm extremely grateful to them for organizing this conference. What's more to say about this? Because it seems this is not just one more conference. This is, as far as I understand, more or less the first in-person conference, at least at Yale and maybe in some parts of the United States after COVID. Also, so this puts enormous problems to the organizers. And I don't, I'm not sure I'm not sure I know all the problems, but I'm not sure that you somehow see what kind of problems can appear. For example, in order to organize this conference, you need a date. But in order to have a date, you have to be sure that you can travel on this date. That's number one. Number two, even if it would be possible to travel on that date, you have to be sure that this facility, Yale University in this particular case, will allow you to enter this facility, which, for example, you wouldn't be able to do this a couple months ago, just not possible. And so this is a kind of problems with which the organizers deal. And so this goes well beyond of the usual conference, so to speak. So I would like to thank again the organizers for doing this so great and doing this under so unusual circumstances. And again, as I said, it seems to me this is probably, at least in the US, probably the first conference, at least I know, which is big, in person, and was organized. So I wanted to thank the organizers for incredible job they did. So second, I wanted what?
I was hoping for a response.
Give me a chance. The second thing, so I want to thank the participants. And I'm extremely happy to see lots of my friends here. And I'm also extremely happy to see so many young people here whom I didn't know or don't know or didn't know before. And this is great because it's young people who's going to drive the subjects later on. And I'm very happy you came and everybody came in spite of COVID. And so thank you very much for all of you for coming to this conference. And finally, this conference, the name is something like On Crossroads of Something. And when originally the idea appeared, the idea of this conference is due to Daiping Wang. And then 3 years ago, I think precisely 3 years ago, it was presented to me by Daiping and Linghui. And I originally thought that that's actually not possible. And I have to decline because first of all, I will not survive this. But more importantly, I wanted to see different subjects I like, maybe excluding arithmetic. But then when you go to the talks, people need to enjoy them, but the people speak different languages. And so it has to be connected, but on the other hand, it's very difficult. But in the end of the day, it turns out that just the opposite happens, at least to me, that the talks were actually sort of internally connected, and I understood lots of things which I did not even expect to understand. See so many connections essentially every day between things I kind of didn't see connections before. So this is due to the speakers. So if speakers would just take random subject, I think this wouldn't happen. But somehow the speakers were very careful about choosing the subjects. And in the end of the day, at least for me, this was absolutely great. So I want to thank the speakers, first of all, that they agree to talk, and those who came and those who spoke in Zoom. I understand how difficult it is to come. Secondly, so I want to thank everybody for agreeing to give a talk. And for those who came, I want to thank you for your bravery that you came in the time of coronavirus here and gave these talks. And I want to thank you also for the talks you gave, because as I said, at least for me, it connects many things which I didn't understand before into kind of, one picture. And for me, it was really great. So thank you very much for all of you, for all of that.
Right, we continue with acknowledgements. I want to give an obvious one. I want to thank Sasha for providing us with the opportunity to organize this conference. It covers many subjects, and one of the reasons that it does so is that Sasha's interests are extremely broad. I also would like to thank other people who have made this possible. We have enjoyed generous support from the NSF, from Clay Mass Institute. Yale Mass Department was very supportive. I would like to thank our chairman, Wilhelm Schlag, for his support. And last but not least, I would like to thank our staff members. We have two staff members who work on this conference. It's Amy Davis, and Amy is a person who was handling hotel reservations and who will handle reimbursements. And well, Amy works from home because of COVID. Tishina Harris, our department administrator, was in charge of organizing, things like teas and, ordering various things. For example, I say to get masks. So let's thank them all for the very hard work. And this, I think, finishes the in-person part of the event.
Indeed, everything is finished, but I want to wish you to stay in good health in spite of the fact that you came here.
All right. Let's thank well, everybody.
Next week, we still have Zoom lecture next month.
Because I am having a kind of prolonged like
Please don't do it. Please write me.